Good morning, everybody. Hi, Reiko. Hello.
Good morning.
Morning.
Hey, everybody.
Hi, Matthias.
Hey.
Nice to see you. Okay. Okay. I hope we can do at least the final meeting in presence time. At least.
I really hope so too. But
Yeah.
Yeah.
Okay. We have a couple minutes, so.
Do you guys still have the mask, or in France they removed? You guys too? Okay. Only in the trains and buses we have to put.
now here, everything in Ireland, everything is gone.
Oh.
2-3 weeks ago. Yeah. So no restrictions anymore.
Wow.
Now we still have the mask inside in the building, the green pass to go to the restaurant and so on. But
Okay.
anyway, they hope to remove everything at the end of March because, but infections are growing again. So
Yeah. Same for us.
Yeah.
We don't know the reason, and also the attention now is shared. No more
Yes.
with the COVID, but the war is the
Yeah.
other. Yeah. So
Yeah.
hope, this project going through a very complicated situation.
Indeed, huh? I've never seen such a situation.
Do you have to go to Japan, Reiko, or you did
yeah.
already?
Well, next Monday.
Uh-huh.
Oh,
And because I cannot fly over Russia, so I am seeing the flight is going through very complicated, like Kazakhstan and whatever,
Okay.
and Mongolia, and then so it takes long time.
Yeah.
And Nele from Risa's group is arriving in 2 weeks for a month and a half.
Uh-huh.
It's nice.
It's more or less 10, so I think we can start this second edition of the webinar related to the Inizio project. That we organized this webinar to allow to diffuse the result that we obtain in this project. I just remind for people not involved in the project that this project is founded in the FET Open program of the Horizon 2020 of the European Community. And the aim of this project is to realize CHIR sensor able to enhance discrimination, following all the different steps. So starting from the preparation of the molecular receptor to investigate the integration with the inorganic surface and so on, and finally to the realization of the devices. Okay. Although the last 2 years have been very difficult for the collaboration among the group, it is to note that the groups have been creatively going ahead in the collaboration among the group, even if the exchange of the research have not been too much possible during this period. Anyway, the results are very exciting. And before to go the desk to the different speakers of this webinar that will cover more or less all the morning, today morning, I want to show a video that we have realized in order to communicate the result, the aims of the project to the public society. So it is 2 minutes video, so it's not so long. So I think it didn't waste too much time for the webinar. So I share the video.
Je pense que c'est bon. Hein. Ouais, je vois et tout. Ok, je raccroche.
I hope you can see the video now. Okay.
Currently, we are spreading tons of pesticides out on the ground, 30% of which do not perform their intended purpose. After application, pesticides tend to degrade, with their residues remaining not only in the plants, but also in various environmental matrices. A big problem with pesticides is the chiral compounds created during production. Two things are chiral when they are both mirror images of each other. These are enantiomers. While this may not sound like a big deal, on the molecular level, these seemingly slight differences can have vastly diverse effects on people and the surrounding environment. Generally, while one enantiomer is the active one, the other is often not only an ineffective pesticide, but it could also have more harmful effects. During the production of these compounds, imagine the flipping of a coin. When the coin lands on heads, the active enantiomer is created, but when tails, the inactive appears. This process repeats over and over until we have the final product. So why don't companies remove the inactive enantiomers? The simple answer, money. It's extremely expensive to remove the unwanted compounds from the mix. The health of our planet is not worth sacrificing their bottom line. Since the best solution of creating a single enantiomer compound is not feasible due to its cost intensiveness, Initio steps in with a low-cost alternative. Their process involves using an array of chemical sensors which work like a nose, recognizing the good and the bad enantiomers in pesticides. These sensors monitor different environmental scenarios and provide alarm signals when hazardous chemicals are accumulating and thus jeopardizing the ecosystem. Through the extensive use of these sensors, you can avoid the accumulation and harmful effects of these inactive and toxic enantiomers and contribute to the preservation of the world around us. To find out more and to minimize the risks from toxic enantiomers, visit project-initio.eu.
Okay, this was the video that we have produced, and this video will be posted in the YouTube channel of the project, and will be also sent to the different partners, so you can use it for the communication of the activity of this project. So after that, it is my pleasure to introduce the first speaker of this seminar, which is with Nikita Grover from the Trinity College of Dublin, and she will present the molecular engineering of porphyrins from enhanced inner core interaction. Please, Nikita, this is the desk is yours.
Yeah. Yeah, just a minute. I'm trying to share my screen. Yeah, do you need to allow me or something?
I don't know. Okay. It seems that you are already.
Yeah.
You cannot share the screen?
No, for some reason it doesn't allowing me. Yeah, just a minute.
Okay. Let me ask to the Gabriele who organized the code.
Hi, Nitika. It's probably because you are a guest. Because
okay,
a few people are listed as guests, and that probably doesn't give you permission. So I think he has to change that.
Okay.
Roberto, maybe it's because she's listed as a guest. Only 3 or 4 people I see on the list have guest behind their name. Maybe that limits it. I don't know.
Yeah, okay. Yeah, because when I'm clicking this open share tray, like nothing is working for me. Like, okay, I'm just sending through email. Yeah, sorry about that.
Strano però. Partecipanti c'è scritto. Can you try now if you can share, because I posted you as participant, maybe now you can share.
Yeah, so now that option is gone for me. It says only meeting organizers and presenters can share, but so I cannot click on that. Like,
Okay. No, because I try to change your.
maybe I can quit and join again. Wait.
Okay. No, now I put you as presenters, so I don't know if it is work now or not. Maybe you have to go out and to join again.
Yeah, I will do that here.
Okay. Sorry for that, but with Teams, it is always a problem. Okay. No. So, okay, I will. I obtain your presentation, so now we can try to solve the problem for all the other. Okay, just tell me when you want to move the.
Yeah.
Okay. So you can start. I hope it is possible to see the PowerPoint.
Yeah.
Okay.
Yeah, I can see that. Yeah. Morning, everyone. Sorry about the trouble. And I'm Nitika. I will be talking about molecular engineering of porphyrin for enhanced inner core interactions. Next slide. So yeah, there are some examples of non-planar pi conjugated molecules, and these molecules has some intriguing properties such as three-dimensional structure, specific in host-guest interactions, saddle shape conformation. So till the date, a lot of maybe can you click for the animation? Yeah, next one. So yeah, so till the date, a lot of synthetic strategies has been applied to modify these structures, such as inclusion of methylene moiety to induce a non-planar conformation or introduction of heteroatoms such as nitrogen atom to perturbate the electronics or to create a stimuli responsive behavior. But if we think about all these things, they are already present in a porphyrin moiety. So porphyrin has a pi conjugation. It has a two type of heteroatoms, imine or amine. So now the next question is it possible to create a non-planar conformation in porphyrin? And in one word, the answer is yes. Next slide. So if we see here, a dodeca substituted porphyrin has these peri interactions. So because of these peri interactions, a non-planar conformation induced, as you can see in this animation. Chiral rings are tilted up and down, like from the mean plane. It means the inner core amine and imine both are available for interactions. Maybe click next. So as you can see, if a porphyrin is planar, then inner NHs are buried inside the core and they cannot interact with the substrate. But if you substitute a porphyrin on the periphery, a saddle shape conformation induced, and now these NH moieties are available to interact with the substrates. Next slide, please. So here I would like to discuss these two examples where saddle shape porphyrins act as a functional material. In first case, it's A2B2 type dodeca substituted porphyrin where octamethyl moieties introduce a saddle shape conformation, and when this porphyrin was treated with chiral carboxylic acid, a porphyrin core itself adopt a chiral conformation. After that, when this chiral carboxylic acid was washed away, chiral conformation of porphyrin retained. So it means non-planar porphyrin can adopt a chiral conformation depending on the peripheral substitution. Next, please. And the other example is from our group where different atropisomers of orthoamine substituted porphyrin interact specifically with sulfate and pyrophosphate moiety. In the next presentation, Chris will discuss this in depth, but these two examples gives us an idea introducing saddle shape with appropriate peripheral substitution can force porphyrin to do a specific functions. Next slide, please. So now there are two things, what we know and what we don't know. So what we know, can you click next, please? So what we know is that porphyrin can adopt a saddle shape conformation, and in few cases, not in all cases, in few cases, these saddle shape porphyrin can interact with the specific analytes. So now we have three questions. Is the saddle shape is enough to make a porphyrin a good receptor? If no, then how we can control the receptive nature of porphyrin via peripheral substitution? And third one, is there any way, like relative or direct way, to quantify the tendency of inner NHs or inner N? Next slide, please. So few years back from our group, we had a breakthrough in terms of porphyrin-based organocatalysis, where octa substituted porphyrin like octaethyl tetraphenyl porphyrin, which is a saddle-shaped porphyrin, catalyze this reaction in 80% yield. Can you click that? Yeah, next please. Yeah, next please. So we came up with a potential strategy because in this reaction there is a nucleophile, there is an electrophile, and porphyrin. So we have a catalyst, we have electrophile, and we have a nucleophile. And the most important thing was porphyrin was acting as a bifunctional catalyst. It means both imine and amine, both moieties were interacting with respective nucleophile and electrophile. So maybe this reaction can act as a like a standard, measuring a standard to quantify the tendency of inner core porphyrin, like porphyrin's inner core. So what we thought we will use this reaction as a standard reaction for the quantification, for the relative quantification, obviously. So what we did, we started synthetically varying the beta substitution and meso substitution. And at the end, we introduced a combined beta and meso substitution. Next slide, please. So as you can see in this, as compared to OETPP, this moiety, these slides represent 3 porphyrin moieties where we varied the substitution at mesophenyl position. For example, in first case, we introduced ester groups at the meta position. So what happened when we introduced the ester group, the electron withdrawing ester groups make the porphyrin inner core nucleophile. Porphyrin couldn't activate nucleophile and conversion was 34% only. In the third case, we introduced methoxy group at the meta position. So what happened? Methoxy groups are electron donating, but for some reason at meta position, the electron donating group didn't appear dominant, and we observe only 77% conversion, which is more or less equal to OETPP. But surprisingly, when we put methoxy group at the ortho position, we couldn't see any conversion. We tried this reaction multiple times, but we couldn't see any conversion. The potential reason is that steric effect of 2,6-dimethoxy group changed the angle between porphyrin ring and the phenyl moiety, and the extended pi conjugation become effective, and the receptive nature of amine moieties like N group inside the porphyrin core become less active. Next slide, please. Yeah, so we continued our investigation and we investigated orthoamine substituted, octaethyl porphyrin paramethoxy substituted, and then dimethyl paramethoxy substituted. So in these cases, activity was much better.
Sorry. Sorry for that.
Yeah,
Okay.
next. Yeah, this one. Thank you. So in these cases, activity was much better. We can see the Hammett parameter for the methoxy group, which promoted the electron density, which induced more electron density. It means they make porphyrin core electron rich. So obviously, the amine moiety could activate the nucleophile. It means like the SH to S. So we see when we introduce electron-rich groups at the paraphenyl position, porphyrin become more active. Next slide, please. Yeah, so in this case, we started varying the beta substitution. So we started increasing the length of beta alkyl chains. So in the first case, we introduced this propyl group, and in the second case, we introduced this isobutyl group. So in this case, propyl group didn't show great conversion, only 28% conversion we could see. But in case of isobutyl group, we could see 89% conversion. So what we learn that paramethoxy and isobutyl, those two are substantially increasing the receptive nature of this particular porphyrin towards nucleophile activation. Next click, please. So we've synthesized this porphyrin, which has both combined features of our good porphyrins, like isobutyl groups at the beta position and paramethoxy groups at the meso position. Oh, paramethoxyphenyl group at the meso position. So in this case, we could see the quantitative conversion. So the message is, I think, clear here. Donating group at the meso position and the pocket, the binding pocket, bigger binding pocket from the OETPP. So in our next attempts, next slide, please. What we did, we take OETPP and we take the general base DBU and our good porphyrins, which showed better activity, and we started varying the mole percent. As you can see, OETPP in 0.5 mole percent and 0.25 mole percent, the activity goes down substantially, like goes down. But in case of 2, 3, and 5, in 0.5 mole percent, activity was okay, like still better than OETPP, but activity was not as great as DBU shows. But if you compare 4 and 6 DBU and our best porphyrin, in 0.25 mole percent, DBU didn't show much. I think DBU shows 10% conversion, but our porphyrin, this octa-isobutyl substituted porphyrin, shows 90% conversion. So there has to be some greater effect apart from deprotonation of nucleophile, and we wanted to investigate those effects. So what we did, next slide, please. We did a simple Uvs experiment. So we took our porphyrin, we add nucleophile and record the time-dependent Uvs spectra. So in the spectra A, you can see only in presence of nucleophile only deprotonation happened. But in case of electrophile plus nucleophile, we can see there are two species, like the solid band has like there are like splitted solid band. It means there are two species. So this clearly indicates both moieties are interacting to the porphyrin core and there is equilibrium between these two species. So it means there is some kind of catalytic cycle which is promoted by the porphyrin. Next slide, please. After that, we did the time-dependent screening, and we took our one of our moderate porphyrin and our best porphyrin, and we observed that this porphyrin achieved 100% conversion only in 90 minutes. But on contrary, this metamethoxy porphyrin took 24 hours and only 77% conversion could achieve. After that, we didn't observe any increment in the conversion with time. Next slide, please. So now we came up with a potential mechanism, and I think fortunately we got this crystal structure. So this crystal structure is isobutyl substitution at the beta position. And as you can see in the porphyrin cavity, this protonated core interacts with two species. One has nucleophilic in nature and another is electrophilic in nature. So this crystal structure confirmed our hypothesis, and on the basis of this, we could draw this mechanism where porphyrin interact with the pronucleophile and generate the active nucleophilic species. The protonated porphyrin interact with this electrophile, make a conjugate, and after that, this active nucleophilic species again interact with this conjugate and generate the product. In the whole process, porphyrin remain intact. It undergoes non-covalent interactions, formation of conjugate, activation of nucleophile. So we could regenerate porphyrin over the time, and the pocket size was big enough to accommodate both species. So I think we achieved a free-base porphyrin-based receptor towards a particular nucleophile. Next slide, please. So in summary, what we learned that saddle distortion is required, and substitution with electron donating moieties is required, but the position of substitution plays a crucial role. So in our opinion, para position is the best. Then meta-meta and ortho positions both act similarly, and ortho-ortho-dash position drop down the activity. Apart from that, beta-alkyl chain, the size of beta-alkyl chain also plays an important role. Next slide, please. Yeah, so that's it from my side today, and I would like to convey my thank you for listening, and Professor Matthias Osenge and my co-workers and Project Initio for financial support. Thank you, everyone.
Okay. Thank you, Nikita. I'm sorry for all this problem that we are trying to solve. Okay, I don't know if there are questions from the audience, if they want to pose. If not, we can. We thanks again Nikita for the presentation. We can go to the next speaker, which is Chris Kingsbury, again from the Trinity College, and we present structural chemistry of porphyrin receptor reporters. I don't know if he can share the screen.
I'm going to give it a shot. We'll be hopeful.
Okay, great.
Okay.
I don't know why Teams make this difference, but anyway, okay.
Okay, is it coming through? It's. Can you see my screen now?
Yeah, but it is in the presentation mode. It's just the PowerPoint.
Fantastic. Okay, I can't see you guys, but I think we'll go. Okay, throw it through there. Okay. So, hi everyone. I'm Chris. I've been working with Dr. Senge, and I'm going to be presenting structural chemistry, porphyrin receptor reporters, and how the work that we've been doing on symmetry and molecular chirality, whole molecular chirality, goes to design. All good? All working okay? All right.
We are still at the first slide.
All right. Okay. So you can see my second slide. It's all going okay?
Yeah. Yeah, this is the second slide. Yeah.
Cool. So we've been looking at advancing what we mean by porphyrin receptor design. So Nitka presented some work on how porphyrins are shown to be interacting with a wide range of species. And a lot of the work that I'll be presenting today was done by Carlos Novosia, and his work on engineering these atropisomeric porphyrin receptors. You can see one example here. The ball is simply just a general feature of some analyte. And what we're looking at is expanding the molecular design toolkit, the things we can do, and specifically towards how do we induce a whole molecule chirality such that we can then go and measure properties of that. And it's not just measuring, it's quantifying it as well, so that we can enhance that design motif. Briefly, porphyrins, and this is what I presented last time. The porphyrin ring, the external bonds are relatively invariant, 28 angstroms, and that's true across most of the porphyrin literature. But by changing the meso and beta substituents and changing the identity of the core, we can dramatically alter the shape of the porphyrin aromatic. And here's some examples of how. So the saddle and ruffle shapes are probably the most common, dome shapes as well, and wave being essentially standing waves inside the porphyrin aromatic that distort the molecular framework and allow us to access a lower symmetry than the high D4H symmetry of the porphyrin molecule. And this paper is something we published early last year, essentially going over all of the porphyrin structural literature and how these molecules actually deform, using data to essentially guide our synthetic ideas. If we can introduce one distortion one way and another one another way and combine both motifs, then maybe we can design a chiral molecule. And generally speaking, making chiral porphyrins, we've looked at three approaches. The macrocycle design, which we published the year before last. And that's a lot of work that's been going on in our group, as well as the atropine-isomeric control and the polyporphyrin units, a lot of Victor's work, as well as some emerging work by Nitika, which is very exciting. What I'll be talking about today is, the design of measurable chirality, and how to both rationally get to this state as well as enhance it, and specifically what these insights can mean for emergent chirality in generally organic molecules, not just porphyrins. The questions generally be answered, and I'll look at signal through some of the NMR studies that Cross has done, the data from crystallization surveys. So how do the porphyrins that we've got interact with a wide range of substrates? Our investigations on shape, and a lot of that was new programs and tools and method development that we've gone through. And synthesis is, of course, a very important part, and I really like Mitch's talk. Generally, questions are, how do porphyrins interact with things? Can we control when they interact, how their symmetry changes? And do these studies have implications beyond porphyrins? Firstly, in terms of how these porphyrins will interact with things, we did a study with a large number of really non-standard porphyrin crystallization partners, POMs, as well as other oxyacids and other bifunctional materials in order to generate a supramolecular framework. And we've got a large number of examples here. Generally speaking, these all had a common, very small subset of interaction types, what we're calling I, Y, and X, depending on whether things are interacting with 2, 3, or 4 units. And what you will have seen in Nitka's talk is that interaction with 2 different things allows them to be brought together into a really intrinsic space and allows them to be in a correct arrangement to do things like a proton coupled electron transfer or hydrogen atom transfer, and act effectively as catalysts. In terms of the NMR studies that we've been doing, so a lot of that is focused on these atropisomers. So atropisomer, of course, is when there's restricted rotation about a bond. And in this case, it's the aryl unit that's attached to the porphyrin. From this, we can get our NH2 or NH3 units pointing up and down, and we can get 4 different separable species. Each of these has a different symmetry, and each of those different symmetries will interact differently when it comes into contact with a chiral analyte. Some of those, specifically the alpha-alpha, beta-beta, or alpha-2, beta-2, will have a mirror plane that will lose on interaction with a chiral analyte. And in this case, we're looking at achiral analytes, and we're saying that it's a very, it's a good colorimetric sensor for phosphate anions. But when we move to a chiral analyte, such as this camphor sulfonic acid, we can see in the NMR that previously combined peaks actually split when we have a different ratio of the R and the S isomers. And I'd implore you to go and have a look at this paper. It's a really good one. It's in preprint at the moment. And yeah, symmetry is our lens. So the way that we approach this problem is through looking at the symmetry and the way that we rationalize why we're getting the specific results that we are. And from this, you can see why we need that non-planar porphyrin. On the left, you've got all of your planar porphyrins. On the right, all of your non-planar. And you can see that there's the lower symmetry. The symmetry is already broken, so the work is half done for us. And this is the result that we're getting, which is that upon interaction with our chiral analyte, you're getting a clear splitting of that NMR signal, and it's in that negative part of the NMR spectrum where there's usually not a lot of signal. So this is an incredibly effective, what's called a pro-CSA, chiral solvating agent. And you're getting a linear interaction with the amount of enantiomeric excess. It's about 3 times better than any previous example of this. It's a really exciting result, specifically because the signal that you're seeing is in a part of the spectrum where it basically means that you don't have to do pretreatment as much. Of course, these atropicemers are really important, and one of the other methods we've been doing, a lot of the synthesis work, has been on how do we rationally get to the atropicemers that we want. And this is one example of how we can do that. We can enrich one of the atropicemers of that orthoamine species really quite easily. Back to the shape of porphyrins article. In that, we basically described 4 different approaches to the generation of chiral porphyrins using techniques that were already established. So we would take one for a non-planar, one in the plane, and then we combine them together and say, well, that's how you get a chiral porphyrin. You use 2 proven approaches at the same time. Oh, am I still there? Sorry about that. Can you hear me?
Yes, we can.
Yeah. Still going. Okay. And all of these have been investigated now. And these are, the set approaches. Generally speaking, in terms of chemical graphs, the connected and atoms are functionally invariant. You're not going to change bonds through this host-guest chemistry, but we can look at principal and minor distortions and then biasing things like vibrations above the limit of the granularity of crystallography. And this work is kind of leading into what I've been working on for a little while, which is symmetry coordinate structural decomposition, which is a new programmatic framework for looking at molecules generally. Martin Breuering brought out a really nice program, Porphystruct, which expanded the NSD work that we were doing out to porphyrinoid molecules generally. Our new framework basically works on all molecules. So you're able to rapidly build up a library and a whole database analysis of the distortions of any kind of organic molecule. And that works essentially by looking at the symmetry coordinates, which means that you don't need to know anything about the molecule going in. And if you're interested, you can go and have a look at this website. I'll drop it in the chat later. One of the useful things we've got are these Mondrian diagrams, which allow us to, at a glance, see what the dominant structure is and what the dominant symmetry is at multiple different levels. The questions we really want to answer with this work is, does a host become chiral when a chiral guest is introduced? So specifically for a porphyrin, but also just generally for host guest chemistry. Can you design a molecular chirality based on finding individual motifs inside a structural database? And can you take that data and basically calculate vibrational normal modes directly from data instead of calculating them? The answer to all of those is yes. Here's an example of some calculations that we've been doing on cucurbiturols, so the 6 unit. And you can essentially see that individual clusters will form based on the number of inversions, but that there's actually a large amount of structural variation within an individual cluster type. So even the normal cucurbitural will have a lot of flexibility. And if we specifically go searching for chiral examples, we can see, okay, here's one example where the chirality is the most pronounced. And you can see how did they get there. And it was by binding a pyranate anion in the core that essentially squashed and stretched and twisted the molecule so that you could get to a chiral state. And that was about 20 angstroms of total atomic movement, which is a strongly chiral molecule, we'll say. The Scsd analysis, the program's available from me just by giving me an email, or there's an online framework at sangagroup.eu. And here's just a framework, a flowchart of how everything is calculated. It doesn't rely on a model necessarily, so it's generally applicable across all structural chemistry. It's a very powerful tool for three-dimensional quantitative structure-activity relationships. Generally speaking, we've looked at chromophores, molecular electronics components, catalysts, and common aromatic molecules. And we generally see this hierarchical structure and this power law relationship are general principles of structural chemistry, which we don't believe have been highlighted before. We're also able to interpret these individual structures with Mondrian diagrams and show that even when we've got a molecule which is a dominantly saddle shape, we can identify that, oh, it'll have a small amount of A2 distortion to it. And in the solid state, what we're doing is freezing one element of that vibration, but that vibration is expected to be active in solution. So we're using crystallography to inform the solution state structure. The chiral bias comes from this notion of flexible rigidity, and that's generally applicable across a lot of rigid and semi-rigid molecule. And what we've got is a chirality definition, which is quantitative and essentially equivalent to that concept of helical chirality, but for planar molecules, or formally planar molecules. Just to conclude, we've published that NSD database analysis. We're looking forward to publishing SCSD and the chirality metrics. This porphyrin enantiomeric excess detection apparatus is an incredibly elegant solution to that problem, and we'll be able to push that as a sensing component when an NMR is available. Porphyrins are also very useful synthetic texons. It just remains me to thank the group, specifically Corollis, who's third from the left and just handed in his PhD, very talented chemist, and Matthias, and to everyone for your kind attention. Thank you, guys.
Okay, thank you so much, Chris, for the
No worries.
very interesting presentation. I see two hands raised. So the first is Rina. Do you want to make a question?
Yes, thank you, Chris. Very interesting view on the structures. And I was wondering with this anion complex with cucurbituryl.
Yes.
Can you comment? So anion was achiral, cucurbituryl is achiral. Where from the chirality comes?
So it was an achiral structure, but essentially it's like, have I got an example? Yeah, okay. So it's like a rubber band. What you've got is this, but if you tried to squash it, then you're going to start getting that kind of motion happening. One way or the other, it's random. So it was essentially a random squashing, and the specific rigidity of the macrocycle led to a chiral conformation, but that wasn't directed one way or the other. So both appeared in the crystal structure. But if you can introduce a similar chiral molecule, it'll bias it, so it'll only go one way. And that's, yeah, an incredibly encouraging way of kind of thinking about it.
Okay, so you notice that the conformation can get into chiral form, and it randomly was observed in the crystal structure of this
yes.
Conformation change. Okay, is it? It's interesting. I will chat with you later about it.
Yes,
thank you.
Of course. Yeah.
Okay, Victor, it is your turn.
Yeah. Hi, Chris. So very nice talk. Thank you. So just wondering, Can you connect your approach, this vibrational approach, to some electronic transition, especially in the case of chromophores, like porphyrins?
Somewhat. So there is going to be some element of vibronic coupling. We've been seeing essentially signals in large numbers of molecules, depending on coupling. You'll see either zero or non-zero biased populations. That said, I don't know enough really to say that there's specifically going to be a vibronic equation which is going to relate these terms. Generally speaking, you'd be able to use those distortions as parameters in a vibronic equation, but really it's a little too early to say. I'm not certain.
Yeah, definitely the different distortions should result in a different electronic transition change, I think.
Yes.
But you
whether
cannot.
there's any coupling, I'm not sure.
Okay, thank you.
Okay, thanks again, Chris, for the presentation. So we can move now to the third speaker, which is who is Zakaria Anfar from CNRS, that will present structural chiral and chiral porphyrins around silicon analysis towards new nano chiral sensor. So please,
Thank you.
Zakaria, desk is
Thank
yours.
Can you see my screen?
Yes.
Okay. So thank you, Roberto, for this presentation. My name is Zakaria Anfar. I work as a postdoc in Raiko Oda Group in CNRS. Today I will present what we did in initial project. My presentation is entitled Structured Chiral and Chiral Porphyrin around silicon nanohelices to make some new nanochiral sensors. As you can see here in my slide, the objective of our work an initial project is to combine chiral or achiral porphyrin with chiral silicon nanohelices. We have different templates based on silicon nanohelices. I will explain to you the protocol of preparation of different templates that we have used in this work in the next slide. So, of course, the objective after this combination is to have new nanochiral sensors for sensing of chiral compounds from solution as well as from gaze phases, but also to study some phenomena like chirality induction, chirality transfer, and so on. The first part of my presentation is about the organic and inorganic chiral template preparation. So to do this, we start from this system. Here we have Gemini surfactant positively charged in interaction with titrate. And we know in advance that titrate have original chirality. So once we put this system in water, he can self-assemble it and give use organic helix like this. The problem of this system is that we cannot use it in some extreme condition of temperature, pH, and also in some organic solvents. So what we did is to cover the surface by silica. To do this, we proceed Sol-Gel reaction. Then after the condensation of silica on the surface of helix, we have a new organic inorganic matrix based on silica. Outside and inside, we have the organic system composed of Gemini, titrate, and the cancer as a cancer ion. You can see here the CD profile of the system. We have a very nice CD profile, which means that we can induce the chirality to the chiral surfactant as well as for the whole system. And the chirality of this system is depending on the original chirality of titrate. If we work with the D titrate, we will get left-handed helices, and the opposite for if we work with L. Once we have this matrix, we can prepare other system. I will start by the first one. So you can see here that what we did to have this new system is just to exchange T3 that we have here inside the structure with chloride. The objective or the importance of this matrix is that we don't have anymore the CD signal in the UV range, and we can use this property to see if we can induce chirality to other molecules or not. Once we remove chloride and we put another molecules, we can use this option for this proposed. The second matrix is that we can remove the organic part totally, and we have just inorganic silica with this chiral nanospace here. And also we can use this chiral nanospace, but especially the surface of silica to make some chemical functionalization in the surface and so on, and also to see if we can induce chirality or to control chirality of other system. This is some team image of the change that happened in our structure by going from inorganic-organic matrix, chloride-based matrix, and also for the inorganic matrix with the CD of or this matrix. In the second part, I will talk about the protocol of preparation or integration of porphyrin into our nanohelices template. So in this work, we have used 3 series of porphyrin, the 3 bases one. We have the chiral porphyrin and also the achiral one. Zinc-based porphyrin also. We have the chiral and achiral molecules, and 2 big molecule provided by Porphyrina, based on cucurbitol covalently attached with porphyrin, with or without zinc. For the protocol of preparation, we have 2 methods. So for the first one, we use the chloride-based matrix. For the second one, we use the inorganic matrix. As I showed you before, once we have this new matrix in which we have chloride with Gemini inside and outside we have silica, we know in advance that chloride is negatively charged, and we have porphyrin also with the same charge. So what we did is to exchange chloride by porphyrin and to have our new matrix in which we have porphyrin inside the system or inside nanohelices. For the second one, we make some chemical functionalization in the surface by using APTS to have amine group in the surface of silica. So once we have amine group in the surface of silica, we go to activate porphyrin-based molecules, because we know that once we have carboxylic groups in the surface, we can activate these carboxylic groups after the activation just by mixing this system with the amine functionalized silica. In some experimental condition, we will get covalently bound between our nanohelices and inorganic nanohelices and porphyrin molecules. So now I show you our template that we have prepared, also the protocol of integration of porphyrin. Once we have this system, we go to test the system in terms of industrial selectivity. To do this, we just make a mixture between porphyrin-based nanohelices system with our analyte. For the analyte, we have used a different analyte. In this presentation, I showed just 3, phenylalanine, glutamine, and also arginine for the L and D. So we know the initial concentration of the analyte. We put our powder, then after 1 hour at 20 degrees Celsius, we get the solid phase and the supernatant. Then we measure the concentration of the supernatant by using the calibration curve, and by using this calibration curve, we will have the final concentration, which allow you to determine the percent of removal. So I will go now to the result. I will start by the first system based on this molecule by using ion exchange method. So as I showed you before, we just exchange porphyrin that chloride that we have here inside our structure by porphyrin. Then what we see is that we can induce the chirality to the achiral porphyrin. As you can see here for this one, this molecule and this molecule are not chiral. So we can see in the serrate band of porphyrin a very nice cotton effect, which means that we can induce the chirality to these achiral molecules. We can also control the chirality or the original molecular chirality of other chiral molecules. If you can see here for the L, as example, for the free bases L, the chirality of molecule doesn't matter. Which important is the chirality of helices, which confirm that the topological chirality of our nanohelices take over the molecular chirality of all system. We can see that also the chirality of free bases molecule is more important than the chirality of zinc-based molecules, which confirm that maybe this zinc monoatomic can affect the orientation of porphyrin or the interaction of porphyrin with our silica nanohelices. In terms of application, unfortunately, our system for all systems are not able to make discrimination of both arginine or glutamine in solution. For the second system, then cucurbituril monoconjugated porphyrin derivative, we use the same protocol, of course, exchange to make this new system. As you can see here, we have a very nice cotton effect in the serrate band of HB6U. HB6U, it is the macromolecule that doesn't have zinc with the with opposite value of G factor. We can see at least the same thing for the ZNB6U in interaction with the left-handed helices. But for the right-handed helices, we have the opposite. We have less interaction, and also in the absorbance, you can see here we have less absorbance. So I take the opportunity, and because we have a lot of specialists in porphyrin here, if really zinc can have an effect on the induction of chirality by using our hybrid system, because here we can see that we have less chirality, less absorbance, which means that this molecule doesn't like right-handed helices compared to the left-handed helices. So as a conclusion for this two part, we can say that the chirality of nanohelices control the original chirality of molecules. We can see this here. If we take as example this molecule that have L as original chirality, we can see opposite CD signal with very nice cotton effect, which means that the chirality of helices or the topological chirality of helices is dominant the molecular chirality. We can see also that for a chiral molecule, I take this example, we can conclude that our nanohelices can induce chiral-optical properties to these molecules. We can also conclude that system with a chiral porphyrin have more chirality than system with system that composite of nanohelices with chiral porphyrin. We can conclude also that system with free bases chiral porphyrin have more chirality than system that with zinc-based chiral porphyrin. And also, in the as a last point, we can say that maybe the zinc monoatomic integration in the cucurbituril system can affect the orientation of this porphyrin, which allowed you to have to discriminate this molecule by using our hybrid nanohelices. So I will go now to this part in which we make some covalent grafting of these molecules in our nanohelices, because as I show you before, in terms of application, we are not able to make discrimination of chiral compounds by using this system of ion exchange. So we think that because our receptor is inside silica, maybe some problem happen in terms of diffusion phenomena, because we work in liquid solution, or I don't know. So maybe if we have the receptor or porphyrin outside the surface, we will have better result in terms of ragnication. So to do this, we make covalent grafting of porphyrin outside as well as inside, but especially outside silica, by using just the inorganic silica. So I'll show you before that we have prepared amine functionalized silica, then we work with activated porphyrin to make some covalent grafting of this molecule in the surface of our silica. So by using this new system, we can have better result in terms of selectivity and ragnication ability of nanohelices. But first, you can see here that after the covalent grafting of silica on the surface of porphyrin on the surface of silica, we can have a very nice CD, and also we can conclude that also in covalent grafting, the chirality of helices take over the molecular chirality of the system. Here I show you two examples. I have used right-handed helices in interaction with the zinc-based molecule with D, or with different chirality L and D, and we have the same CD profile, the same cotton effect in the solid band of this molecule. So in terms of enhanced selectivity, as you can see here, this system in interaction with phenylalanine with different chirality S or R, we can have different interactions depending on the nature of the system that we have used. So if we use the right-handed helices with molecule with zinc-based porphyrin molecule that have D chirality, we will this system is able to interact more with R compared to S. And the opposite if we change just the system that we have here. We work with L instead of D. We can see that the system is more interacting with S compared to R. So as a final conclusion, we can say that the final chirality of prepared system depends to three factors: the nature of porphyrin, if we work with chiral or achiral porphyrin, the environment, if we work with zinc-based porphyrin or just the free basis porphyrin, and also the original chirality of helices. For molecule based on cucurbitual system, we can say that our nanospace can discriminate zinc-based cucurbitual based on zinc porphyrin, and also this molecule can interact with left-handed helices more than the right-handed helices. For the covalent grafting method, we can say that we have a very nice system after the grafting of this molecule in the surface, and also the system is able to make some discrimination and selectivity of phenylalanine depending on the original chirality of the system. In the perspective of this work, we want to work with this system and to make some column to test the enhanced selectivity in a big system. And thank you for your attention. And I would thank all the member of our group that work in this project. Thank you.
Thank you, Zakaria, for the nice presentation. I don't know if there are questions from the audience. No, if not, thank you again. So we can move to the next speaker, which is Lucas Ustnul from Taltech, who will present hemicocurbituryl complexes with porphyrin chirality induction and sensing. So,
hello everyone, can you hear me?
Yeah.
Okay, I will try to share my screen then.
Okay.
Okay, so you can see my presentation, right?
Yeah, perfect.
Okay, so hello once again. I work for Professor Rina Af, and in our group we were mainly focused on describing and finding out more about supramolecular properties about our hemicocurbituryls and porphyrins as a potential system for sensing of chiral compounds, because of course a lot of sensors are based mainly on those supramolecular interactions. So the porphyrins were introduced and talked quite a lot in those previous presentations, so I will not talk about them, but I will give you some basic introduction to hemicocurbituryl. So those are macrocyclic compounds, which are sorry, I will put here the pointer. Yeah, okay. So those macrocycles are based on monomeric units, which every time contains urea moiety, and then those are connected through the methionine bridges. And you can see that there is every time some sort of cavity, which typically binds anions, and the size of this cavity is dependent on the number of monomeric units in the cycle. And this one on the left was first prepared, and it's kind of the simplest hemicocurbituryl which you can find. But in our case, we are using those cyclohexano hemicocurbituryls. So you can see that here is this cyclohexano group. And this macrocycle is chiral, thanks to the stereogenic centers here. And we are able to prepare its RR and also SS enantiomer. And we are able to prepare in gram scales this 6-membered macrocycle and 8-membered macrocycle. On previous initio webinar, I was talking mainly about this research where we studied simple zinc porphyrins and their interaction with our macrocycles, where we found out that they indeed produced complexes with quite good association constants. And what was interesting, we were able to fit even up to 3 association constants. Why 3? It will become obvious from the next slide, where you can see crystal structures. So in this structure with the 6-membered macrocycle, you can see nicely that the interaction is between the metal core, between the zinc and the carbonyl oxygen. And then when you look here to the structure of 8-membered macrocycle, it has stoichiometry 2:1, but in overall, one macrocycle is surrounded by 4 porphyrins, so it's easy to imagine that even in solution, it could form up to 4:1 stoichiometric complex. However, fitting of those higher stoichiometries is really difficult, and this 3:1 complex seem to be fitting really reasonably. Moreover, we could then use the same binding model for 8-membered macrocycle and 6-membered macrocycle, which is a bit smaller, so we assume that it can accommodate in solution those 3 guests, or 3 porphyrins to be more specific. But what is most interesting on this system, and why I'm reminding it, is that we used those porphyrins which are completely non-chiral, so they are fairly cheap and they are commercially available. But upon interaction with macrocycle, you can see that in the solid band region, there is induced circular dichroism. So it means there is a transfer of chirality from macrocycle to porphyrin. And that's also about what the previous speakers were talking a bit. And we assume, as the circular dichroism is visible, but nothing really huge, that it's caused by some sort of distortion of a plane of the porphyrin, as it was discussed by Chris. And when we had this system, we realized, okay, the macrocycle has still empty cavity. If we have just one-to-one complex, then there is plenty of carbonyl groups which can bind some other guests. So, of course, this is suitable for building some ternary complex where the third component could be our chiral guest, chiral pollutant, which we want to recognize. But for practical use, we need to understand what those two compounds can really interact and in what media they can do that. For porphyrin, it's quite well described in literature, but for Hemichoker bacterials, which were invented in our group, we had still quite some holes in the knowledge what can be precisely bound. So that's what is about this first publication which I'm going to talk about, and it was focused on various organic guests and their binding in chloroform. So first experiment which we did, we took this larger 8-membered macrocycle and we were adding to it those guests 1 to 9, which are various more or less polar organic guests, and we were checking its NMR, and for the guests 1 to 7, we did not see any change in the spectra of macrocycle, but for those phenols, we saw some slight changes, and from the fact which signals were shifting, we could also clearly say that this interaction is not happening inside the cavity, but everything is bound from the outside of the macrocycle. So we assume that for having some interaction, we need to have a hydrogen bond donor. So then we enlarged our scope for those guests, which were from the groups of thiophenols, phenols, carboxylic acids, and also sulfonic acids. And we took this 6-membered macrocycle to have a little bit less of binding sites. And here you can already see the order in which those compounds were binding in chloroform. And as I said, we have 6 binding sites. So we tried different binding models, even this our 3-to-1 binding model, but there was no binding model which could fit the titration curves with all these guests, because some of them were binding really weak and some of them were already quite strong. So we chose to compare them just in a qualitative manner, because we assume that all the guests are bound in a similar or same mechanism. Therefore, just the shape of the curve, like more it's curved, then stronger should be the binding. And of course, we wanted to relate it to some real numbers. So we calculated this Hirschfeld partial atomic charges for the protons, which should be the hydrogen bond donors. And indeed, this order of binding kind of more or less fits with those numbers, but there is some outliners, which we assume are mainly caused due to the fact that some of those guests, they can dimerize themselves like carboxylic acids, and then some of them are rather bulky, so we assume that there can be some sterical hindrance. Anyway, this study improved a lot our understanding how organic guests can be bound to our macrocycle and what could be the potential guests for this sensing system. And now the next article which I want to talk about is about bisphospherins. So first of all, a little bit what is bisphospherin. As you can see, it's a compound where 2 porphyrin cores are connected with some linker. In this case, we were using this simple ethene bridge. And this compound in solvent, when it's pure, has this thin conformation because there's like pi-pi stacking between the porphyrins. And then upon addition of ligand or guest, it can go into this tweezer-like conformation or in this anti-conformation. And in the case when your guest is chiral, then this conformation can be locked in some preferred direction. So it looks like here on the picture with this diamino cyclohexane. And in such a case, we can have really nice induced CD. And it's even well described in literature that based on if your CD, induced CD is a positive sign or negative sign, if it means that it's organized clockwise or counterclockwise. And this, of course, works the best in this tweezer conformation, but also in anti-conformation, there can be some preferred direction of a twist based on like hindrance between the substituents of your guest and substituents on the Bispothering. So it's a great system itself for recognizing chiral compounds, and we were interested how it will interact with our macrocycle, and we were also interested if due to some, okay, I can't remember how it's called, but it doesn't matter. Let's continue. So here's the results of titrations. So we had every time Bispothering, and we were adding macrocycles. On the left is with 6-membered, on the right with the 8-membered macrocycle. And here you can already notice that this one signal of porphyrin was shifting first in one direction and then back to another direction, which is clear signal that it can't be just simple one-to-one binding. And we were able to fit this data with 2-to-1 binding. Then this other proton and its shifting and splitting is suggesting that there is happening opening of this thin conformation, and it goes into tweezer or into anti. You can't like really differentiate to which one of these it goes. And then with 8-membered macrocycle, the shifts were similar, but their extent was lower. So we just assume that the 8-membered is binding weaker. So more or less in NMR, except the strength of binding, the behavior looked the same. But in UVs, we could see clear differences. So after addition of the same excess of the macrocycles, when there was not much of a change in the spectra upon further additions, we could see that this shape corresponds what is in literature described for the tweezer complex. But for 8-membered, in the same conditions, same concentrations, it looked very different. And later we found out that there is some additional effects which are happening in time. So now I will talk about time-dependent measurements, where every time first spectra is just a pure Bis-Zinc OEP, then right after addition of macrocycle, and then after some time development. And for 6-membered macrocycle, you can see that the change in time is very small, but for 8-membered macrocycle, the first change upon addition was not really big, and then it drops significantly within 2 hours, and then the changes in time are finished roughly after 24 hours when there is a new band around this like 450 nanometers. When we look in CD spectra, then we can see the similar things. So for the 6-membered macrocycle, there is no changes in time, whereas for 8-membered, there is a bit change in time. And what is also interesting to comment the shape of CD itself. So for 6-membered macrocycle, we can clearly see that there is happening this exciton coupling, which is typical for the tweezer conformation of Bispothering. Whereas here, it looks rather more simple, similar to what we saw before with just regular zinc OEP. So we assume that with 8-membered, the CD is caused just by those distortion of porphyrin plane rather than some preferred conformational distortion. And now what was really interesting experiment was the same type of time-dependent measurement in fluorescence, where for 6-membered you can see that the shape is more or less the same. There is a little bit new bump, which would again suggest that it goes into a tweezer shape, and there is no change in time. But for 8-membered, it gave us quite a lot of information, because you can see there's basically no change right after the addition of the macrocycles. So we assume that the first binding is happening the way that the bisporphyrin is still in this syn conformation. And then in time, it has to be opening up, because this new spectra, how it looks after 24 hours, resembles a lot just normal zinc OEP, and it's complex with the macrocycle. So from this, it's clear that this bisporphyrin is opening into this anti-conformation in time. So the thing is now that as it took so long time, this stabilization of the process, we were thinking by what it can be caused. And when you take a look in literature, you will find out that for porphyrins, there is described a lot of systems where, or if you find some systems where the changes are happening in time within like hours or days, it's usually related to some sort of aggregation. So we actually assume that maybe there is some equilibria between this syn and anti-complex, which maybe prefers much more this syn, but in anti, it can then form some sort of more or less random aggregates. We don't know how those aggregates would exactly look like, but you can imagine that there is a space for that, and it could be connected this way. So, and it would make sense that then this aggregation process is actually stabilizing this anti-conformation, so it slowly turns from the syn to anti. So now I will just try to conclude this particular work. So with 6-membered macrocycle, we have first quite strong association constant, and it goes to this tweezer shape complex. And then the second binding of macrocycle is much weaker. So there is negative cooperativity, and this is also in good agreement with previously studied some small guests where if it went through the tweezer, then first binding was much stronger than the second one. And then with the 8-membered macrocycle, we assume that first binding is happening in the form that there is still this syn conformation of bisporphyrin, and then it's opening into an anti-conformation, and probably it is driven by formation of aggregate. Conclusions. In general, we found out that our macrocycle has a good fit with the porphyrin from the point of size, and it can cause distortion of the porphyrins in the way that they will become chiral. So this system could work as a sensor for chiral molecules using the spectroscopic properties of porphyrin and the chirality of the macrocycle. Then we looked into the binding of macrocycle more deeply, and we found out that in organic media, it binds preferably from outside on its carbonyl groups. So the good guests are such guests which are good hydrogen bond donors. And finally, by studying this bis-zinc OEP complexes, we found out that this bis-zinc OEP can recognize between the different sizes of macrocycles, and this differentiation can be caused only by their different size and shape, because otherwise those macrocycles are chemically equivalent. In the end, I would like to thank Professor Rina Af and Professor Viktor Borovkov to bringing me to this interesting project. Then I want to point out my PhD student Marko Shakarashvili, who was the main author for this bisporphyrin article, which was a lot of work. Then all the other people who I worked with for financial support, and finally, thank you for your attention.
Okay. Thank you so much, Lucas, for the nice presentation. So I don't know if there are questions from the audience. If not, we thanks again, Lucas, and then we move to the next speaker. We are perfectly on time. Thanks to all the speakers. So the next speaker is Nele Conrad, again from Caltech. Will present Urea organocatalysis as emerging chiral pollutants en route to porphyrin-based chiroptical sensing. Okay, Nel, the desk is yours.
Hello, thank you. So you all see my slides, yes?
Yes.
Okay, thank you. Very nice. As it was mentioned, my name is Nele Conrad and I am Professor Riina Av's PhD student. And today I will give you some overview about our work in thiourea organocatalysts as emerging chiral pollutants. So here is the outline of my talk. First, I will give you a short introduction to the topic. Then we will discuss the toxicity and binding studies. And in the end, I will summarize everything with conclusions. To start with, the organocatalysis is a much used and useful field in order to obtain chiral organic molecules. In year 2019, UPAC listed the organocatalysis and the selective organocatalysis as one of the top 10 emerging technologies in chemistry. Last year,
sorry, there is a problem with the microphone. I don't know, but I hear a very strong noise.
Okay. Is it still there?
It's still disturbed. I don't know why. There is maybe some contact that is not working.
Okay, I will try maybe.
Because at the beginning it was okay.
Okay, I will try another microphone I have. Just a moment, sorry. How about this one?
Much better. Perfect.
Okay, thank you.
Okay.
Let's go on with this one then. Okay, so as I was saying, last year, as we all probably know, Benjamin List and David Macmillan got the Nobel Prize in Chemistry for the development of asymmetric organocatalysis. So we can safely say that organocatalysis is a hot and promising topic, but we also have to look from the other side as well. The question is, are all organocatalysts so environmentally benign as believed? And the real answer is that we don't know. There is a previous study that has been conducted on such functionalized thiourea. The authors measured the toxicity on human cell lines. And what they found out that this thiourea is actually a toxic compound. So this brings us to our thiourea and organocatalysts toxicity studies. The toxicity studies were conducted in collaboration with National Institute of Chemical Physics and Biophysics. And in these studies, we checked the toxicity to marine bacteria Vibrio fischeri, which have a bioluminescent effect, and we did inhibition tests. In these tests, we used altogether 5 different organocatalysts. For organocatalyst 1A, we checked both enantiomers. And what we could see from the test results is that the organocatalysts 1A and 1D that have trifluoromethyl groups are actually have EC50 values between 7 to 8, which means that they can be classified as toxic compounds. If we take a look on organocatalyst 1C and 1P, we didn't see any toxic effect on the maximum tested concentrations. Another thing to note here is that between enantiomers of organocatalyst 1A, we didn't notice any difference of toxicity. So we can take this knowledge into account, and also because our initial project aim is to develop sensors for such toxic compounds, we moved on further to try to search for a solution. For sensing the shown organocatalysts, we have chosen to use zinc porphyrins as sensors. Zinc porphyrins are, as it was shown already previously, highly colorful, and they have very unique spectral properties. And it is known that with amine-containing guests, zinc porphyrins form such host-guest complexes where the amino group is coordinating on zinc ion. In our studies, we have used 9 different zinc porphyrins and 4 different organocatalysts. The porphyrin P9 was provided to us by Professor Senge's group. In collaboration with Professor Kari's group, we were able to obtain a single crystal X-ray structure of a complex between porphyrin P5 and guest 1B. So this crystal structure is important because it confirms our assume that the complexation is happening via zinc and amino group coordination. There, as you can see, there is also thiourea moiety in the organocatalyst, and we were afraid that perhaps this complexation could happen also via the thiourea coordination to zinc, but thanks to this crystal structure, we got confirmed the complexation mechanism. In order to determine association constants and the binding strength, we performed Uvs titrations. In here you can see example titration of porphyrin B5 and guest 1A. So what you can see here is the upon complexation, free porphyrins Urea band is decreasing and complex porphyrin is increasing. And similar decrease and increase is also visible in Q bands. To calculate our association constant, we take these 2 maxima here. So the decrease of Urea band and increase of complex, and we fit them to obtain our association constant. Out of the studied porphyrins, porphyrins P2 to P7 are different from each other only from the para-substituent of the porphyrins phenyl group. And all these different substituents affect the electronegativity of the zinc ion. Electronegativity can be also described by, of a phenyl group can be also described by Hammett's constants. And we have fitted, we have plotted our association constant values and the Hammett parameters of the substituents on one graph. We have done this to 3 different organocatalysts, so organocatalyst 1C, 1B, and 1A. And as you can see, mostly these association constants tend to follow the expected trend. However, there are 2 association association constants and two complexes that do not follow the trend, that are much weaker binding than they were expected. And these are with the organocatalyst 1A and with porphyrins P6 and P7. As you can see here, P6 and P7 have strong electron withdrawing substituents. In order to understand why exactly such thing happened, we performed Dft calculations. So from our previous studies, we have already performed Dft calculations of complex 1A P3, which had association constant, which was expectable from our Hammett graph. And now to go further, we have done Dft calculations on complex 1A P6, which was the more weakly binding complex. And what we can see from this calculations is that if you compare the main conformers of the complexes, then you can see that of 1A P3 complex, the aryl groups of porphyrin and the guest have face-to-face orientation. Whereas if you take a look at this 1A P6 complex, which was more weakly binding, the aryl group of porphyrin and our guest have D-shaped orientation. It is already previously known that when both the aromatics have strong electron withdrawing groups, they prefer to take T-shaped orientation. Such orientation also affects our complexes conformation.
Currently,
and
we are
it
spreading
also
tons of pesticides.
Elongates the bond between zinc and amino group. As you can also see from the calculations, in the complex of 1A P6, the zinc amino bond has been prolonged a little. And this longer bond also supports the fact that the complexation is weaker. And in here you can see CD spectra, experimental CD spectra for both of the complexes, and we can see clearly that the CD, the chirality is very different based on the conformation. For all the studied complexes, chiroptical analysis was performed, and we measured for all the complexes CD spectrum. As you can see, almost all complexes possess some sort of chirality. And if we take under a look for one porphyrin, let's say porphyrin P3, and we compare its different complexes with different three organocatalysts, 1A, 1B, and 1C, then what we can see from here is that the complex with 1A and P3 strongly stands out among others. It has a very different CD spectrum, and this organocatalyst 1A was the one that was also toxic from our studies. And if we go further and take only one guest molecule, one organocatalyst, 1A, and compare different CD spectra of this 1A with all the different 9 zinc porphyrins, then what we can see is that mostly the trend is this, that the more electron accepting our zinc ion becomes, the more positive the CD signal goes. So at first we start off with this fully negative CD signal. We get if we get to more electron accepting porphyrin, we will get to bisignate signal until we will have only positive CD signal. To conclude the results I have shown in here, we have performed toxicity studies on marine bacteria Vibrio fischeri. And from these toxicity studies, we can say that organocatalysts 1A and 1D can be considered as emerging chiral pollutants. And for that, we need a reliable instrumental detection method. We have done comprehensive binding and chiroptical studies, and from our studies taken into account both the binding strength and the chiroptical outcome, we have recommended to use some porphyrins to sense some specific pollutants. So for organocatalyst 1A, we would recommend to use porphyrins P2 and P3, and for organocatalyst 1D, we would recommend to use porphyrin P8. The all presented results are also published in journal Chemosensors. I would also like to thank all the co-authors and our collaborators from Initium. And also another paper connected to Initio has been published in journal Symmetry. In this article, sensors of chiral compounds are discussed, and also thanks for all the collaborators. And I would like to thank all our people and collaborators who have helped us and financial support. Thank you for the attention.
Thank you, Nell, for the kind presentation. Are there questions from the audience? Okay. No, so we can move to the next speaker, which is still from the Taltech group, Tatiana Shalima. I hope I pronounced it well. Removal of small electron-rich organic compounds from water via host gas binding with hemicoker vitrials. Please, Tatiana, the desk is yours.
Just a moment. Can you see my slides?
Yes, perfect.
Okay, great, thank you. So thank you for the kind introduction. My name is Tatiana Shalima, and I am a PhD student from Professor Rina Av's group. And today I would like to present our recent results on removal of small electron-rich organic compounds from water by host gas binding with hemicoker materials. In our research group, we synthesize new supramolecular receptors, and then we study the host gas chemistry. And in today's talk, I would like to focus on their binding properties that can find real-life applications, for example, for capturing and removing small heterocycles from water. Amongst these, there is particular interest towards sulfur-containing heterocycles, because on one hand, they are widely occurring in nature and they can exhibit biological activity. For example, lipoic acid that is chiral and exists in, as two stereoisomers. On another hand, some sulfur-containing heterocycles can be found as toxic pollutants. There is a nice example of degradation products of sulfur mustard, which can be found in water around the dumping sites of warfare. And recent reports are suggesting that their harmful effect on environment and toxicity can be even more serious than sulfur mustard itself. So Lukáš already introduced you to the supramolecular receptors synthesized in our group, which are cyclic xenohemicoker materials. For simplicity, from now on, I will refer to them as to
Tons
6
of pesticides
and 8
out on the
membered
ground,
macrocycles.
30% of which
And
do
so
not
far, it
perform
has
their
already been established that they are able to form inclusion complexes with different anions. And also they are able to bind non-dissociated acids on the outer surface via formation of hydrogen bonds. However, we were curious to see whether our macrocycles can also be used to form complexes with other neutral compounds. The Hemichoker materials, in our case, they are bearing an electron deficient cavity, which is very likely to accommodate species that are possessing a negative charge. That's why the scope of neutral guests chosen for these studies included heterocycles that would possess either sulfur or oxygen or nitrogen heteroatoms, which are electron rich. And our study began with the discovery of inclusion complexes between the macrocycle and a series of small heterocyclic guests, forming one-to-one inclusion complexes in solid state. It happened in the in methanol solutions of macrocycles in the high excess of guests, and it was thoroughly characterized by single crystal X-ray diffraction. So that served as a solid proof that such phenomenon indeed takes place, and we decided to process with this topic. The next step included complexation studies in solution, which was carried out as screening of different guests by proton NMR in methanol. In this study, we followed the characteristic signal of 2-axial proton, which is positioned inside the cavity of the macrocycle. And in case of encapsulating the guest, there should be a change in the chemical shift of this proton. And as you can see on the spectra, some guests indeed induced quite a noticeable change.
Currently,
so we further determined association constants for selected guests. For that, we were using two different techniques, which were isothermal titration calorimetry and proton NMR titrations. And our results showed that indeed the association strength is correlating with the screening results, and 1,3-dithiolane was exhibiting the strongest binding to the macrocycle. And then we also decided to check how binding occurs in different media. So for the guest that showed the strongest binding, we decided to investigate the process in methanol, and as well as methanol and water mixtures in different ratios. And we discovered that in higher percentage of water, the binding increases. So bearing in mind that the macrocycles are almost insoluble in water, we decided to check whether it's possible to apply them in solid phase extraction. In solid phase extraction experiments, it was a crucial step to produce fine powder out of the macrocycle, which was done with the help of milling the compound in the shaker mill, which would produce fine particles, most of which would be below 5 micrometers. And then the solid macrocyclic material would be dispersed in an aqueous solution of guest compound, which will be stirred, forming a suspension that contains solid host compound, dissolved guest, and also host guest complex, which would exist as a solid. Then the mixture would be separated, producing the solid free host and host guest complex, and the remaining guest would stay in solution. And the concentration of guest could be analyzed by a suitable method. So the guest concentration was determined by either direct UV-Vis spectrophotometry or by HPLC UV. And the change of guest concentration before and after extraction would be expressed as removal percentage. In the extraction experiments, we studied the removal of a number of guests, which included the previously investigated sulfur and oxygen containing heterocycles, then lipoic acid, which also bears a fragment with sulfur heteroatoms, and also two imidazoles that possess nitrogens. So the results revealed that the extraction was carried out as follows. So we would use the 8-membered macrocycles. Macrocycles are a promising sorbent material, but also we would study the behavior of its smaller homologue, which has a smaller cavity, which doesn't really allow formation of inclusion complex as a control material. And also we were using commercially available silicarbon TH90 as a reference material which is commonly used. So the data that we collected showed that 8-membered macrocycle can indeed extract different guests from water with quite good sorption efficiency. On this graph, sorption efficiency is expressed in logarithmic scale as the mass of sorbed guest per surface area of the host material. Unfortunately, there was no binding observed for the nitrogen-containing heterocycles because they're quite polar and perhaps it's more favorable for them to just stay in solution. However, we noticed that there is a very important characteristic of our macrocycle, which is selectivity. So compared to that performed by commercially available charcoal, the macrocycle actually can differentiate between different guests because it shows different affinity to those. And this affinity correlates nicely with the partition coefficient values for different guests. So the more hydrophobic is the guest, the stronger would be the binding and the more efficient would be the removal. So it allowed us to make an important conclusion that guest hydrophobicity is actually the main driving force in this process. We also decided to study the reusability of macrocycle acting as a sorbent. And in the experiments of 1,3-diethylene removal, we proved that a very simple washing and drying procedure of the macrocyclic material allows to perform multiple subsequent extraction cycles without significant loss in removal efficiency. However, it was important for us to understand the complexation that stands behind this removal. So we wanted to find out whether it's happening just to physiosorption on the surface of the macrocyclic material, or it's the consequence of the inclusion complex formation. So we decided to perform thermogravimetric analysis of the solid material after extraction of 1,3-diethylene. And the idea here is that upon heating, the sample, namely the sulfur-containing guest, starts to decompose at certain temperature. And in the case of pure 1,3-diethylene, as well as 1,3-diethylene together with the 6-membered macrocycle after extraction, the decomposition would start at around the same temperature. However, in the case of 8-membered macrocycle, which is holding the guest that was extracted from water, the evolution of this characteristic fragment would appear at significantly different temperature, and the shift in this temperature would serve as a confirmation of actually inclusion complex formation, because that means that the guest is held inside much stronger and it requires higher temperature to start destroying it. And most likely in the case of 6-membered macrocycle, it's not the case because the cavity is significantly smaller and it cannot accommodate the guest inside. And then we had an idea inspired by one recent paper to study solid state, to study complex formation in solid state by preparing mechanically agitated complexes. We performed these studies for those guests that were efficiently removed from water, and we chose 1,3-diethylene and lipoic acid. And in this study, the idea was that we would mill together the host and guest compounds, so the macrocycle and one of the guests, in the presence of small amount of water. Thus, it would model the extraction process, which is happening during removal of heterocycles from water, but in solid state. And then we would analyze the obtained complexes by solid state NMR. As reference samples, we used the mixtures that would be obtained by just mixing those two together without applying any additional mechanical force. And so the recorded spectra showed quite significant changes for signals 2 and 6. And these are the carbons of the macrocycle that are positioned inside the cavity. And again, they serve as the indicator of inclusion process. And there were no such changes observed for either physical mixtures without applying additional force, or for the milled mixture with the 6-membered macrocycle. So again, we got quite a solid proof that inclusion actually happens. And a few words about the extraction of lipoic acid. As mentioned before, this was a chiral guest, so it was very important to investigate whether chiral macrocycle can distinguish between different kinds of acid. And at first, we saw that there was certain difference between the removal rate by different enantiomers of macrocycles. However, when we conducted extraction in a higher excess of host molecules, we had to conclude that the difference is negligible, and maybe it's just correlating with the physical properties of the powder. So we had to conclude that there was no enantiomer discrimination in this case. To sum up, we have discovered that 8-membered cyclohexane Hemichoker butyryl forms inclusion complexes with small electron-rich sulfur and oxygen-containing heterocycles, and it can be used as a material that efficiently removes sulfur-containing compounds from water. And altogether, it makes it a promising reusable sorbent material that can be applied in solid phase extraction and maybe find application in such fields as water purification, or it can also serve as a complementary tool in analysis. And it's my great pleasure to share that the results were recently published in Frontiers in Chemistry journal. I'm very grateful to all the co-authors, as well as Caltech Supramolecular Chemistry Group, and all the funding sources that made this research possible. And I would like to thank you for your attention.
Okay, thanks, Tatiana, for the presentation. I see you have changed the stairs at the end.
Yes.
Okay. I don't know if there are questions from the audience. Okay, no. So thanks again, Tatiana, for the presentation. So we can move to the next speaker, which is Michela Ottolini. It's come from Unisalento, but it is now at the Trinity College in Dublin. So one example of the researcher is changing the project, even in these difficult conditions. So she will present a spectroscopic investigation on supramolecular arrangement of porphyrin derivatives in host-guest interaction, which is the work she's done there. Okay.
Okay, you can see my presentation?
Yes, perfect.
Okay, good morning, everybody. Thank you, Professor Palese, for my introduction. As the professor said, I'm Michela Ottolini and I'm a PhD student at the University of Salento. And since October 2021, I'm working in Professor Seng's group at the Trinity College Dublin. Both groups are involved in initial project. Professor Seng's group activities are focused on synthesis of the new porphyrin derivatives, whilst Prof. Wallis' group work aimed on immobilization of these derivatives as active layers in sensing devices. And for me, it's as represented a perfect opportunity to expand my technical and communication skills. In Dublin, my research work has been focused on the characterization of the derivatives shown in this slide. And these preliminary characterizations are essential for the next immobilization on solid support. In particular, I performed a series of spectroscopy measurements in solution in different situations in presence of metal ions reported in the slide. This is important in the initial context, considering that it is well known that metal coordination of porphyrin core can strongly influence the supramolecular aggregation, favoring or not, for instance, the formation of chiral aggregates. The binding of the metal has been studied by UV spectroscopy and fluorescence spectroscopy in all cases, and it is clear that both the spectrum of electronic absorption and emissions change dramatically, both in a number of Q bands and the relative position and intensity of the SORE band. For example, in this case, the zinc, the SORE band splits into two new bands, while the Q bands change. The presence of the metal completely changes the spectral profile and emission intensity. While the copper, if compared with to zinc, has a quite different behavior, and the fluorescence show as a shift of the emissions band. All this is synonymous with a strong interaction between the metal and the derivative, so strong to affect porphyrin spectroscopy behavior and most probably supramolecular arrangements. The perchloride acid was used. Perchloride acid was used to roll out protonation and deprotonation events, and interestingly, this was confirmed with the NMR. This technique was used to study the sites of the interaction between porphyrin and investigated ions, including metal and chloride. Hence, first we performed the titration with TbClO4, and we can see that the mesophenyl splits and beta proton splits and NH downfield shifted. It means ClO4 attached at NH-CO band of the lateral moiety and not involving all the porphyrin core. While when we performed the titration with the CdClO4, in addition to above-mentioned changes, we observed the shift in inner NH, and hence there is no covalent interaction between MClO4 and porphyrin, suggesting the involvement of the core in a good agreement with the previous spectroscopy evidences. So the next steps with regard to the finalizing of the characterization of interaction between metal ions and porphyrin derivative, Cuban derivatives, and the future deposition in Lecce for the study of thin solid film. In the meantime, the physical chemics group activities continued for the deposition and the characterization of hybrid films, incorporating both chiral nanoribbons synthesized in the group of Professor Oda and the different porphyrin derivatives. And in particular, the attention was focused on two achiral porphyrins and two chiral derivatives synthesized by Professor Seng's group and Professor Paules's group. And all the derivatives bear a carboxyl moiety in order to exploit electrostatic interaction with the amine group of the nanoribbons. The Langmuir-Schaffer approach was chosen for thin film deposition from the air-water subphase interface, and this is an approach ensuring high control of the deposition parameters and a good reproducibility of the preferential molecular organization within the film. In fact, the supramolecular duct is formed directly at the air-water interface by dissolving the nanoribbons into the subphase, allowing the interaction with the floating molecules and the deposition of the hybrid layers. For the first achiral derivative, take in account this is a morphology of just one layer of porphyrin monitored by means of FM characterization. For hybrid layers, we observed a dramatic change of morphology of the film that clearly incorporates of L nanoribbons and a clear chirality induction in agreement with the nanoribbons chirality was individuated in the case of the hybrid layer, and we can see the red spectrum. Again, also for this achiral porphyrin, the incorporation on nanoribbons was first demonstrated by IFM, and these are the images for the film of just porphyrin, and these are the IFM images for the supramolecular duct. In this case, the preferential orientation of the nanoribbons perpendicular to motion, the motion direction was also found, and even when nanoribbons concentration was increased. And the circular dichroism spectrum acquired here in Trinity College evidenced a clear chirality induction for the hybrid obtained in presence of L nanoribbons. We can see the red spectrum. And these observations were confirmed by means an ellipsometer approach ad hoc modified in University of Salento for the analysis of optical activity of very thin films. The optical activity of the hybrid film with L nanoribbons, just 2 layers, has been clearly measured. We can see the red spectrum. The L form of chosen chiral porphyrins was demonstrated to incorporate nanoribbons, both L and D, within the film, and the presence of the helix strongly influenced the chiral feature of the films. Also, the form of the porphyrin incorporates the helix, as you can see the IFM. In this case, the porphyrin didn't show CD signals, which appears of the hybrid layers confirming chirality induction. So the importance of obtaining chiral films or modulating the chirality features of the film is related to need of developing active layers for chiral discrimination. Preliminary tests, sensing tests were carried out on the films, obtaining starting from the achiral derivatives bearing the Cuban moiety, and the tyrosine was chosen since it is an amino acid belonging to the synthetic pathway of levodopa, and with a very similar chemical structure. So we demonstrated by fluorescence spectroscopy that only an active layer incorporating L nanoribbons, which exceeded the chiral features, is able to discriminate between D and L enantiometers of tyrosine, fluorescence enhancement, and quenching respectively. So there are very fascinating preliminary results which promoted us to conclude the characterization of all the film that I showed in this presentation in order to choose the best active layers for L-DOPA and D-DOPA recognitions. Thus, we reported several hybrid films utilizing porphyrin, helix, and hemicocorbituril synthesized by most of partners involved in initial project, with the final aim that carry out sensing experiments in Tor Vergata. So thank you so much for your attention, and let me ask you 1 more minute of your attention.
Okay, well, thank you, Michela. Yes, Michela has prepared this slide for the summer school, which will be held here in during the last week of June. And I already contacted you, and just wish to know if from your groups somebody will take part in the school. I remember that it is not any registration fee to be paid by participants, by delegates, and it will be held from the 26th to the 30th of June. The first day is a Sunday, 26th, and just we shall have the presentation and welcome coffee will come brindisi to the school, and we have just obtained also the participation of Nick Kotov from USA to the summer school, and we are still in contact with Litz Marsan in order to try to have also his participation to the summer school. Now, I need to know who is coming among PhD students, postdocs, and so on from your groups. I have to communicate since probably 40 students will take part to the summer school. And then I just wish to know if you prefer to have the initial meeting on Thursday, 30th, or on July 1st. It is just to organize everything to discuss in the best way the results of the initial project. Well, but it is more important to speak about the results obtained by Michela in her investigations. Thank you for your attention.
Ludovico, sorry, but there is a website where to register students, or
well, we are in contact with our university in order to create the platform. Please, 1 week and it will be available. Of course, we hope to have some students from the groups involved in the initial project.
Okay, for sure. And it depends on the June 30 June afternoon when the school ends. In the afternoon, or so if we have all the afternoon, we can
at noon.
Okay, so we can fix also the 5th June afternoon for our meeting. I think it's enough.
Okay,
but it's open to the different option. I mean, no problem for that. Okay, thanks, Ludovico. There are questions from the Michela talk. Okay, if not, we can move to the next speaker. Thanks, Michela. So the next speaker is Kai Truong from the Uvs University. Sorry for the pronunciation. Who will present solid state host gas studies with target analytes.
Yes, thank you very much. Can you see my screen?
Yes, perfect.
Okay, perfect. Yes. Yeah, thank you very much, Roberto, for the nice introduction. Yes, I'm from Uvs. I'm a postdoc here, and my name is Kaini Truong, if you haven't known that. Yes, we here at Uvs, we do structural characterization of the chiral systems, which have been synthesized by the initial collaborators. And now today I want to give a talk about the solid state host gas studies with now the target analytes. But before that, I want to give you a short recap what we have done before. So first, we did the structural characterization of the provided chiral hemicocubital system synthesized by TTU in Tallinn. They have been introduced before. So it was the all RR, all SS cyclohexanocubiturils with the 8 and 6 membered rings. But also biotin urals. Then another big component was the commercially and non-commercially porphyrin or metalloporphyrins. These have been provided by TTU in Tallinn, TCD in Dublin, but also one lately characterized structure from UNITOF. It was a chiral proline functionalized zinc porphyrin derivatives, and we might see that one later in the next talk. Yeah, this was the first year. The second year was then we focused on the host gas binding of all those components to a 2 or 3 component system. We have seen before from Tatiana that it is very important to get the information about the binding behavior. So we have been able to get some information that there is some selective binding of the ions. There are some binding of small heterocyclic molecules inside the macrocycles, only in the 8-membered ring, but there is some binding happening. But if we are going to bigger molecules, like here on the right side, the quinine, it is a little bit more complicated. And we could also see that it's not going inside the cavity anymore, but we have different binding modes, which is quite interesting. But I will talk about this a little bit later. Then what we have seen also in Neil's talk previously, that we have done host gas binding of metalloporphyrins and commercially available analytes. They could be chiral, they could not be chiral, but yeah, we had a few examples there as well. The next step, which was a huge package, was the synthesis of the building blocks of hemicocubiturils and metalloporphyrins. They could be covalent and non-covalent. We have only been able to get crystal structures of the non-covalent building blocks. Here you can see some examples of 1-to-1 discrete complexes, 1-to-2 discrete complexes, but also some one-dimensional coordination polymer. At the end of last year, we were also we were able to get some ternary complexes. Unfortunately, they were not yet the target analytes, but yeah, I will come to this point later. So all these structures that I have talked until now, and also in the previous webinar or presentations that we had with our initial collaborators, were just showing the general motive that those host guests are coordinating, but in general, it is a little bit more complicated. And I just want to show it to you with this example. So we have seen this structure previously. So this is the all RR 8-membered macrocycle with quinine. We could see that there's a direct binding of the quinine to the macrocycle over a hydrogen bond. We could also see that the vinyl group is dipping inside, or dipping at least at the rim of the macrocycle. But what I have left out in this part is that I have left out quite a lot of solvent molecules. And I have, I could find the solvent molecules for this example because it was a quite good resolution data. So we have quite a lot of water molecules, co-crystallized water molecules. Those water molecules do a lot of intermolecular interactions. We have OHO interactions between the water molecules with the macrocycle. They also do some hydrogen bonding to the quinine itself. And what we have seen before was also that the quinine does a direct hydrogen bonding to the macrocycle. So it is everything which we see in solid state is a little bit more complicated than I'm always showing on the figures. So this is what you have to keep in mind. Most of the structures are also always have some kind of solvent molecules, co-crystallized solvent molecules, which stabilizes the structures itself, but most of them are not as stable as we would want to have them. So the model analytes here are the ones that I have tried next to quinine with different functional groups. As you can see, there are quite a few. Unfortunately, although I have tried several crystallization methods, conditions, quinine was the only structure that we were successfully with X-ray diffraction. So going to the target molecules, these ones were the ones that we proposed with in our proposal. I had first to look which ones were feasible because here in Finland, some drugs are not that easy available. So you need a special form. So I just focused on these six compounds. So we got the insecticide, some drugs like naproxen, ibuprofen, the metallochlor, salbutamol, and corallose. And I did first two component systems, so meaning I got these molecules together with the hemicocubiturils. I have used the 6-membered and the 8-membered, but I also have used the SS isomers. But this is just a scheme to show you what I have done. So from previous reactions or from the first 2 years, we knew that the binding only is possible if we just use methanol. If we use any other solvent or a mixture of a solvent, we will not get, it will not form, so there will be no binding. These are just 4 possible binding modes. And the first example where we were able to get a crystal structure was with S-naproxen in methanol, of course with high excess of naproxen. It crystallizes as you can see, naproxen is not bound directly to the macrocycle. It is bridged via water molecules. So in this case, it does kind of like a dimeric structure with nice hydrogen bonds. We also have a very weak interaction here, CHO hydrogen bonding, if you want to go like this. And if we extend the structure, we get a nice one-dimensional hydrogen bonded polymeric structure of this. The second example that we were able to get a crystal structure with was with chloralose. Here you could see that we have quite a lot of different functional groups, a lot of hydroxy groups, which would also again favors the formation of hydrogen bonds. In this case, we could see again that a lot of hydrogen bonds are forming. However, the chlorulose is not bound directly over a classical OHO bond, but a bifurcated CHO. And if we extend the structure, which I have tried to visualize here, it crystallizes quite interestingly. We get kind of a nanotube structure. If you, this is a top view here, down here, where 6 chlorulose molecules are bond via hydrogen bonds. Then those ones are again, each of the chlorulose is bound to a macrocycle, which forms like this kind of a star structure, nanotube structure. And those stars nanostructures are again linked together in the C direction via water molecules to the next layer and the next layer and the next layer. Unfortunately, these two were the only examples out of the 6 that we have tried. The next step was, of course, to do a complexation study of ternary complexes. So we used the zinc TTP tetraphenylphosphine, which is the most available, commercially available, but also in quantity available metalloporphyrin. We did again the same systems like before with the 8-membered macrocycle and the 6 guests. I just wanted to repeat again that we have been previously been successful to crystallize some structures. Here are the X-ray structures of the 2,5-dihydrofuran, 3,4-dihydrofuran, ethyl benzene, and eugenol. So we knew that it was possible, and in these structures we could also confirm the binding modes which we have previously have seen. So we could see that, for example, smaller molecules, it could be solvent molecules, it could be heterocyclic molecules, they could bind inside the macrocycle. Those structures are always stabilized via hydrogen bonds, if it's water molecules, or it could be also methanol molecules. But if it's getting a bit bigger than the ones, the dihydrofurans, they cannot bind anymore within the macrocycles, and we will find some intramolecular interactions outside of the macrocycle or with the porphyrin itself via CH-pi stacking or something like this. Unfortunately, we were not successful to get any ternary complexes with the chiral analytes. There could be different reasons. We tried several combinations of solvents, temperatures. We have also tried these 5 other analytes that we have obtained from Tallinn. But the only thing that we were able to get or confirm the previous results were the 2 component systems featuring zinc TTP, and this is the table of 8 different X-ray structures in a different, crystallizing differently with different co-formers or no conformers, different temperatures. So it is really difficult to predict what structure we get. But in general, no matter what stoichiometry we get, if we use those conditions, usually we get some kind of a 2-to-1, 1-to-1 discrete complexes with a lot of co-crystallized solvents again. For example, this one's with methanol water. Sometimes it's also DCM methanol. We have also seen now what we have seen previously with the magnesium derivatives, that it can also form a one-dimensional coordination polymer. This is the helical type of a 1D strand, which the co-former as naproxen. The same thing we have also observed again later with the, if we use the all SS isomer with the S-ibuprofen that naproxen, that it forms again this now in the other handed helix. Yeah, as a summary, solid state structures are not easy to predict. It is really depending on what we use. So the solvent is playing a huge factor, the temperature, the co-formers, even small changes. If you change something like the concentration, it will give a different product. But in general, we had a big library of hemicokumulus that we could use and analyze. The same with porphyrins and metalloporphyrins. We got also from Tallinn a few hemicocubital porphyrin conjugates. However, we were not been able to crystallize or get the X-ray structure, neither the conjugate itself or the guests. However, we got some information from the complexation studies from 2 and 3 component systems, and hopefully those X-ray structures helped us a little bit to understand the recognition event between the chiral receptor and target analytes, although we already know that the actual binding or the actual recognition event will not happen in solid state, but in solution or gas phase. So it might be that we could see the binding all, or we can detect them via solution or gas phase, but with solids in solid state, it is sometimes difficult to get the structure itself. The same happens with structures if we want to measure it not only with single crystal diffraction, but powder diffraction or solid state NMR. They are getting more and more complicated if we add a component more. So this was also one of the things which was hard for us to achieve. At the end, I would like to thank the group here in Uvs Experiment, my supervisor Kari Rissan, who couldn't attend today, unfortunately. You guys, all collaborators from the Initio project, as well as the audience here. Thank you. If you have any questions, feel free to ask.
Okay, thanks Guy for the presentation. Noela Stefanelli or Rom Tor Vergata, who will present the bright side of merging porphyrin and proline for chiral sensor development.
Did you see the presentation?
Yes.
Okay. So, hi to everyone. It's a pleasure for me to close this interesting webinar for our project. And I decided to share with you some aspects, some old and some newest, to the use of for the use of these specific porphyrin derivatives, which is we can say that probably this is one of the most studied system during the project, as Michaela and Zakaria just reported this morning. So I will explain why and how we use these prolinated porphyrins both in solution and in solid state to develop some chiral materials. So all of us probably work with porphyrin, and probably I think love the richness of properties of this kind of macrocycles. So it's not needed to underline all the properties of this macrocycle to have a different chemistry, coordination abilities, and photophysical properties for target applications above all. At the beginning of our studies, several years ago, we decided to insert stereogenic information on the macrocycle to construct several architectures with chiral fashions. So we selected among the aminoacidic groups the proline. Why? Because this kind of amino acid is conformationally rigid and is very robust to racemization. So the enantiomers we can have the final stage of the synthesis is very stable. So for the preparation, we can count on different protocols typical of peptide chemistry. So the introduction of the chiral moiety on the porphyrin skeleton is very easy and can give our desired chiral porphyrin derivatives that can be assembled in different ways. For example, to have a chiral porphyrin assemblies in solution, but also can be arranged in different ways, also on different nanostructures, as for example nanoparticles. So the marriage between these two units can be very easily, and two derivatives can be obtained depending on the starting porphyrin reagent. We can exploit both the amino groups and the carboxylic group on the phenyl position of the porphyrins, and coupling with the proline amino acid. So we can have at the final stage two different derivatives which are different from the one from each other for the for the presence of a different charge located on the peripheral position of the macrocycle. This is a structural difference which have a deep impact on the aggregation behavior of the porphyrins, but is not the unique difference we can have among the derivatives. In fact, this kind of conjugate offer many options to vary the amphiphilic character, for example, with the charged groups on the proline residue, the coordination abilities of the macrocycles, so inserting different metals into the inner core of the macrocycle, and of course we can also vary the stereogenic information on the proline, choosing different enantiomers of the proline to be coupled with the porphyrins, and also the localization of the chiral center by changing the type of connectivity between the microcycle and the proline unit. All this variation brought to a distinctive aggregation behavior of the derivatives in solution. We can assemble these derivatives using the so-called good-bad co-solvent protocols, which consists in the dissolution of the monomers of the porphyrins in a good solvent and the addition of the proper amount of water that trigger the aggregation of the macrocycle by hydrophobic effect. The advantage of using porphyrins in this kind of study relies on the possibility to monitoring and have a lot of information about the aggregation and the type of aggregation in solution by using a collection of spectroscopic technique like UV visible RLS, CD, of course, which gave us different information about the specificity, the aggregation size, the aggregate size, sorry, and of course the supramolecular chirality displayed by these systems. So over the years we play a lot. We have played a lot with this kind of macrocycles. At the beginning, fixing the proline residue on the peripheral position of the macrocycle and changing different structural parameter and experimental condition to drive the formation of specific aggregates in solution. So the chiral porphyrin assemblies can be finally achieved combining structural features as well as experimental conditions like bulk solvent mixture composition or also structural parameters like the metal coordinated, the proline type charges, sorry, on the periphery and so on. Recently, we also are able to, we were able to have the porphyrin enantiomers L and D with an ionic charge on the proline, and we also noticed that changing, for example, the metal inserted onto the macrocycle, we can have a system with a completely different chirality and morphology, of course. So different, very different behaviors are observed for the free bases, the zinc complex, and only recently also the cobalt was the new entry for our investigation that seems to have a completely different behavior in solution in water and ethanol mixture. So also the use of external chiral inducer like ligands can have a deep impact on the aggregates morphology, which changed from a fractal type when the chiral amines are not added on the solution during aggregation to micro rods when they are used as co-solutes during the aggregation. So in solution, we have many options to vary the structures and also the experimental condition to modulate in some ways the system we have to obtain, we want to obtain. But of course, so we have also to develop, and this is particular important for the development of chiral sensors, to develop this kind of materials also for solid state. Of course, it's possible to deposit on glass, for example, the chiral aggregates obtained in solution as just described, but this is not very convenient because of the time-consuming procedure that allow the formation of chiral aggregates in solution that requires mostly 1 or 2 weeks. So we have turned our attention towards the other systems to obtain chiral films, chiral materials at solid state, and I discuss with you today the possibility to have chiral films depositing by job casting monomers of these porphyrins on glass, and also the use of hybrid materials for sensoristic point for the sensoristic field. So we decided to investigate the possibility to directly deposit on glass the porphyrins, the chiral porphyrins, of course, on glass, and verify if the chiral information on the protein can give films with chiroptical properties.
Rispetto a quanto ce n'è dentro.
And it was a nice surprise that using toluene as solvents, we have rapidly and in a very easy way the formation on glass surface of films with high and high signal, CD signal, and with the signal that are highly reproducibility. So we comparing the spectra obtained for the films casted on glass with the same system, with the same enantiomers aggregating in solution, we can see some similarity about between the two different systems, but and so we can ascribe the aggregation of the monomers onto the surface to a similar mechanism occurring in solution, in the hydroalcoholic solution, that see the coordination of the carboxylated group of the proline to the zinc ion on the porphyrins. This is the driving force for the formation of this kind of aggregates in solution, but probably it's the same driving force for the evolution of chirality also at solid state. So we developed a rapid and easy to make preparation of chiral films onto a low cost and transparent substrate, which is glass. So which is very useful for practical application, for example, for optical measurements. And these systems, these films are also highly fluorescent, so and are also stable in water, so they can be potentially used for the detection of chiral pollutants in liquid. We investigated so in detail the reason of this kind of results, analyzing what happens in solution and also on the surface. Of course, because the concentration and the type of solvent nature used for the deposition is crucial, is very important to determine the chiral character of the films. Of course, also the nature and some parameters like hydrophilic or hydrophobic character or roughness of the surface surface is also important. So we analyze first of all the solution. We modify the kind of solvent used for the deposition. So we use toluene and ethanol and THF for the deposition, and we explore also a range of concentration here indicated. Well, we obtain good results chiral films only in the case of the use of toluene for this kind of macrocycles, while the use of THF and ethanol didn't give chiral films on glass. So we performed some DLS analysis to analyze what happens inside the solution of the macrocycles, and we discovered that the use when the monomers, the porphyrin monomers, are dissolved in toluene, also varying the concentration, we detect some protoaggregates inside the solution with this kind of dimensions, which has not been observed when we use ethanol and also THF. So probably we conclude that this kind of protoaggregates, the oligomeric structures inside the solution, can trigger the aggregation of the monomers onto the solution when the solvent evaporates on the glass. The different solvents used for the deposition also explain and confirm our hypothesis on the kind of interactions inside the films to give the chiral character of the films, since the zinc ion is bad solvated in toluene respect with ethanol and THFs, so is prone to the coordination of the carboxylator of the other monomers during the aggregation. So probably THF and ethanol are strong competitors for the aminoacidic residue and didn't give a specific readout of the stereogenic information of the macrocycle. Of course, proline residue is necessary for the achievements of chiral film in solution, on solid state, since the use of the achiral porphyrins in toluene did not give aggregates both in solution and in solid state. And so what happens on the substrate? I have to confess that at the beginning of our study, we had results strictly dependent on the type of glass we use for the deposition. We use a lot of glasses in our lab, but sometimes we had the good results with depositing the toluene solution of both enantiomers, and sometimes no. We did not give any kind of chiral films. So we decided to analyze in detail the surface we used for the deposition, and we observed that by AFM images that the surfaces used for the deposition is very different. And we had the chiral films only when the glass slide used for the deposition is ultra flat, when the surface is not so irregular and the roughness is not so high, which is the typical case of the commercial microscope glass slide, which had an irregular surfaces and roughness higher. So we probably think that the porphyrin deposition onto a flat surface can facilitate the chiral organization of the macrocycle during the solvent evaporation. And this arrangement is we can say that is hampered on this kind of surface. This is irregular and hampers the film growth in a chiral fashion. So this is the story. Probably we think that nucleation seeds are formed in toluene solution before the deposition, and this occurs only when toluene is used as solvents. Probably because toluene has a non-coordinating character, possesses also the highest surface tension and the lowest vapor pressure that favors the film adhesion to the substrate, and prevent also the fast evaporation of the solvent during the deposition, the film formation. So the film has the time enough to assemble in the right way, in a specific way on the surface. And also the glass roughness is has to be necessarily minor than 10 nanometers for the effective chiral arrangement of the macrocycles onto the surface. So moving on, the possibility to use these derivatives also for the preparation of hybrid system conjugating porphyrins with inorganic nanoparticles. We choose zinc oxide nanoparticle and silica nanoparticles as hybrid system for the development of gas sensors. Gas sensors array are just used in our laboratory using different chiral macrocycles, but in all the cases the macrocycle have to possess the carboxylic group to find the nanoparticles efficiently. So several works are just published on the use of different porphyrinoids, porphyrins, and corrols for the gas sensor array development. And we also present recently work that use these porphyrins in connection with the zinc oxide nanoparticles, which results which can be deposited on QMB surface and give some enantiomer discrimination toward limonene. So we are able to combine chiral porphyrins also with silica nanoparticles, so not only with the silica nanohelices that Zakaria just reported this morning. In this case, the grafting is not covalent, but we can absorb and attach the macrocycles on the silica nanoparticles by electrostatic interactions, and the systems are very stable, and when deposited on the glass give CD spectra that are very similar to those just reported in the case of glass on the films of the monomers onto glass. So also these systems can be used, for example, for optical measurements. passing to the conjugation with the zinc oxide nanoparticles, as just said, we were able to use the hybrid system of porphyrins and zinc oxide nanoparticles on QMB chiral sensors, and we found that the chiral systems displayed high enantiomer discrimination toward limonins, even if compared with the chiral aggregates from ethanol water solution simply casted on the quartz surface, or the chiral monomers. So the hybrid system seems to have a good impact on the stereoselectivity of the materials. Another way to exploit the zinc oxide nanoparticles is also the conductometric transduction mechanism. So we prepared hybrid systems containing these porphyrins and zinc oxide nanoparticles by varying the functionalization method, using two main different procedures. And the reason is that previous study carried out by our group found that the procedure of preparation deeply affects the morphology of the obtained nanoparticles, and above all, the corresponding sensitivity of the hybrid system toward different classes of gaseous analytes. So we want to, in this preliminary results that I'm showing you, we want to investigate the difference in the preparation procedure for the hybrid materials. So comparing the procedure, the one-pot nanoparticles growth, where porphyrins is added at the beginning of the preparation of the nanoparticles, which is different from the post-functionalization of porphyrins, which is added at the final stage of the synthesis. Fixing the enantiomer of the porphyrins, but varying also the method, the method coordinating inside the porphyrins. So we prepared this kind of materials, and we drop casted the solution, the toluene solution of this macrocycle, these nanoparticles, onto interdigitated electrodes for the construction of conductometric arrays. In this case, it's possible to activate the response of the nanoparticle by using light. So we use this experimental setup for our measurement, where the liquid volatile compounds tested are inserted in the sensor chamber by using mass flow controllers. So the gas is diluted until in the chamber by using synthetic air, and the variation of resistance of the materials is recorded by a digital multimeter. So we have different response depending on both the procedure used and the metal insert in the macrocycle. When the electrodes are, when only, this is the case of water, response of the system. When we use only light to record the resistance of the material, we observe that the difference in procedure is deeply affects the conductivity of the materials. In this case, the resistance decrease more for the materials prepared with the post-functionalization procedure. While the materials prepared with the co-grow have higher response to the gases compared with the other. So and also we can see that zinc porphyrin complexes show the higher responses to water vapors. So there is a difference between the metal insert in the macrocycle. So light is able to activate the response and also the chemical sensitivity of the prepared materials. We also we also investigated others derivatives. In particular, we decided to verify the influence, of course, of the chiral in this case the type of procedure for the preparation of the materials, and we were able to detect that the materials deposited on the electrode surface have chiral characters, that so the enantiomer pairs have almost specular CD spectra, which is not a result. Preliminary results are here reported for the measurement with this kind of box, ethanol and water, in the concentration range here indicated. We work and the potential of this system, and we can conclude that of the proline residue can allow the charge injection from the porphyrins to the zinc nanoparticle, even if it's not conjugated, and of course for the development of chemo-resistant resistance. So in particular, the increased sensitivity toward means this other classes of box can be a reason for choosing these systems respect to, for example, QMB sensors, whose transduction mechanism is intrinsically less specific. We can avoid this porphyrin function mechanism to develop chiral sensors. So I conclude this contribution to thank all the collaborators for this work, especially Roberto and Ilaria, that are now particularly involved in the experiments relating to the aggregation in solution and the development of chiral sensors. And of course, all of you for your kind attentions.
Okay, thanks Manuela for the presentation. Are there questions? Okay, if not, I want to thank all the speakers for of this webinar. I hope we have presented the advancement that we have obtained in this project. I hope to see most of you in person in Lecce for the school, and we posted the link of the video to in the chat of this meeting, so you can see the video in this through this link, or if you need the file for the video for the communication and dissemination activity, you just have to ask us, so we can make available in the also in the Inizio project website. Okay, so thank you again, and okay, we shall see next time, okay, hopefully in person. Okay.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Bye. Bye.
Bye.
Bye, everyone.